Okay, so let's start. So this is just, oh, you don't see it. What's happening? Okay, that's better. Just to remind you that the exams are out, you can come to the office hours or recitation to pick it up, ask questions, look at the solution, make sure that you understand and agree with everything. 2, projects. I want to meet with all the teams. Please come to my office hours. If you cannot make the office hours, drop me an email and we'll schedule some other times. But I do want to talk to all of you as soon as possible. What makes things a little bit harder is that next week I will not be here. So the 2 lectures next week are going to be devoted to neural networks. One of my students is going to give it. It's going to be excellent lectures, so please come. Tell your friends to come. He's taught this before, so don't miss these lectures. But it's going to make it harder, so come today. I'm going to stay late if you want to talk about the projects. Other than that, we'll have to schedule next week. The only day possible is Friday. and then the week after that. And by that week, I really want to finish meeting with all of you. Problem set. Okay. So we are delaying the problem set number 3, and we'll release it only next week, probably Tuesday evening after the first lecture of next week, because it's going to be largely about neural networks. I think these are all my announcements. Questions? Yeah. 5. So officially 5 to 6. If you cannot make 5 to 6, I'm going to stay late and meet with you. So don't come at 8, but yes.
I tried looking through the slides, the PDFs, and a lot of the symbols are still off. I don't know if I need to install some.
Which lecture is?
The SVM lecture.
I'll check it again. Yeah, I see it okay, but I know that there have been problems with some symbols. I'll check it. If you can send me specific numbers, that would be helpful. Slide numbers, but I'll check it. Yeah. So say it again. What was released?
The last problem set was released a bit late, like
Yeah.
a few days or so, and I think we had like a lot of other students that were having a lot of midterms and exams, and we didn't get any extra time, so we would have really appreciated it being released a little earlier. So like for this problem set, is it possible to release it earlier, even though the material has been covered? So like maybe some students.
It's not going to give you anything. So the issue is when we delayed the previous problem set, we took off material from the homework, so you didn't lose anything. If at all, you gained some, because we cut some stuff from it. The material that homework 3 is going to cover is what I'm going to talk about today and what we're going to talk about next week. So it's not going to give, maybe 1 or 2 of you will get something from it and will be able to start working on it, but the majority will not. So we're going to adjust the time accordingly. It's just I'm running a little bit slower than I expected to when I designed the syllabus and the dates. Yes?
So when will the
Excuse me?
So when will the problems have
I'm not sure exactly. It's going to be around 10 days or so from the day we release it. So we'll announce it. We'll put it on the web. Other questions? Okay, so let's see, what did we do last time? We talked about SVM. Specifically, we talked about hard SVM optimization. This was the optimization problem that we derived, and we explained it as an outcome, immediate outcome of the generalization theory that we talked about before, minimizing the size of W, L2 of W, subject to all the examples are separated by a margin of 1. We mentioned briefly that this is really a quadratic optimization problem, but it has a unique solution. The fact that it's a quadratic optimization problem for many years resulted in the fact that computing SVM or learning SVM was slow, but I'm going to get to it in a few minutes. We then talked about duality. We said that really what's important are those points that are exactly on the hyperplane Wx equal 1 and Wx equal minus 1. And these are called support vector. And we quoted this theorem that say that W, the weight vector that we're going to learn, really is defined uniquely by those examples that reside on these 2 lines. So these alpha coefficients are going to be 0 for all these points here that really do not serve to define W, and it's going to be non-zero only for those that stay on the line, and this is why these are called support vector machines. So really W, as you've seen in the case of perceptron, can be spanned as a linear combination of examples. We then move to talk about soft SVM. Yes?
So are we like throwing away a lot of the examples then? Are we only looking at the examples that are like really close to the time?
The algorithm looks at everything because it doesn't know ahead of time what's going to be on the boundary.
But it only adjusts the weight vector based on this close.
Not at the beginning, right? So at the beginning, you can start in a random situation, say perpendicular to the final W, and you're going to touch other examples and update based on it. It's going to be a gradient descent algorithm in principle. But eventually, what will happen is that these will not matter. During learning, they do matter, or some of them matter.
So we're only looking at like, I guess like a few examples at a time. Or like only at
So that depends really on the algorithm. But if you think about the gradient descent type algorithm, you can either look at one example at a time, stochastic gradient descent algorithm, or maybe a mini batch where you look at a few examples at a time. At the beginning, you don't know what matters. So you take a collection of examples, you compute the gradient, you update, and so on. Eventually, you realize that some of these examples you can throw away, and they will not matter to W. So there are many algorithms, and some of them are more clever in how they treat the examples. But in principle, I cannot tell you ahead of time who's going to be the support vector, and therefore I cannot throw examples ahead of time. So I'm not planning to talk a lot about algorithms because in principle you're going to use a package to do it. I will show one slide and you'll see that you actually know the algorithm already. But this is an important conceptual thing that really the final weight vector, the optimal weight vector, is spanned by the important examples. We then move to talk about soft SVM, where the relaxation is really a function of the realization that the data may not be linearly separable, and therefore we want to allow some slack variable, and we allow this psi I per example, and we say, well, we only care about this YW transpose X being greater than 1 minus this psi. So that's a relaxation. And that means that our optimization problem now becomes optimize the size of W and also the size of the psi I, or the overall size of the psi I. And this C parameter serves to decide which of these components you care about more. And this is what's being tuned when you learn SVM, this C parameter, the balance between these two components. And then, again, the constraints you have changed to be this. We moved from there to basically see that we've seen this before, because we can rewrite this essentially this way, where the psi I is bounded from below by 1 minus the dot product times y, which is another way of saying the psi I are really the hinge loss of the example. So we were looking at this picture and basically said, really what's happening here is we optimize two components, a sum of two components. One of them has to do with the size of W that we agreed last time has to do with our generalization abilities. It's directly related to the margin of the linear function. And the second one is the errors that we're going to make. How do we measure the error? Via the hinge loss. Okay, so these are the two components that I talked about. So one of them is really the empirical loss, the errors that we're incurring. The second one is the regularization, the control on the capacity, the size of the weight vector. And we said that we can, basically we've seen this before. In principle, all learning algorithms will have this form, and you have the flexibility in principle to replace the loss function and to replace the way you regularize. So SVM really is part of a family of algorithms that we've seen before. Okay, so just to see kind of the picture, you can think about it this way. Here is data. There's another picture another version of the picture that I've shown before. I have, on the left side here, I have training data. On the right side, I have test data, imagined test data. And in this case, what I'm trying to do is I'm trying to fit the classifier so that I will not make any mistake on the training data. And you can see on the left that there are no mistakes between the triangles and the circles. On the other hand, I do make some mistakes on the test data. Another case, another option could be that I'm trying to fit a thicker separator on the left side. This thicker separator does make some mistakes. You can see at least one triangle that kind of moved to the other side. The advantage here is that now I'm doing better on the test data. Of course, this is just an example, but this is kind of the idea that we want to accomplish by learning these thick separators and allowing ourselves to even make mistakes in training. Yes?
Is there any way to sort of predetermine what the balance between thickness of the separator and size is?
So, yeah, so this is the C. So learning SVM basically is going to run this algorithm. Where is it? Is going to run this algorithm and tune C as you go. So you'll have a development set, and you'll tune C, and C is exactly the balance between what do you care more about, mistakes on the training data, which is measured by this component, or generalization, which is measured by this component.
I was not clear in my question. I was saying, is there some sort of standard way to predetermine the balance, or is it only just by...
What do you mean pre? Before what? Before you see the data? Or what do you mean predetermine?
Is there any way even just from... Is the only way to find that the best value for that parameter just by tuning it?
It's data dependent, right? So if I give you data that is very easily linearly separable, it's one thing. If the data is not linearly separable, it's another thing. So it's really a data dependent thing. You have to tune this parameter. You don't know ahead of time what to do. Okay, so basically that's the picture. There is also a demo there that goes to the liblinear demo, which is liblinear is the best library for support vector machines. If people want to use support vector machines, I would recommend highly playing with this. It exists in multiple languages, C, but also Java and Python. Okay, so a word about optimization. So as I said, you don't really care about it because you're not going to do it yourself. It's interesting historically to realize that when SVM started in the late 80s, it was extremely slow. The reason is that the solvers actually solve a quadratic programming problem. Later on, people realized that actually you can do it with gradient descent. And there's multiple families of gradient descent algorithms, some in the primal, some in the dual. Probably the most commonly used today is an algorithm that works in the dual called dual coordinate descent. And these are actually very, very fast algorithms. So today, SVM is as fast as all the other linear algorithms. One reason for it is, I'm not going to do the math here, is that it's really a gradient descent algorithm. And if you try to take this objective function at the top here that we showed before and develop the gradient descent, you'll get this algorithm, which is very, very similar to everything you've seen before. It's really a version of perceptron, if you want, where C is plugged in here, and we also add some weight, some learning rate to the W's to the update. So you don't just take the W as is. But it's really very, very similar, and it shouldn't be surprising to you that it's very similar. Now, the algorithm as written here doesn't have a convergence proof because it's a stochastic gradient descent problem. You have to tweak it a little bit. There is a version of it that it's called Pegasus, and multiple other versions for which you can actually show convergence. By the way, the same kind of algorithm can be, as we said, has a dual version. And in this dual version, you can use kernels. Again, I'm not going to talk about the technical details written here in one slide. In the slides from last lecture, from Tuesday, the second half of the slides is a tutorial on optimization. So if you really want to understand how the optimization works and the theory behind SVM, there are about 20 slides there that you can go over with some pointers, but you don't really need to know this. Okay, questions? Okay, so where are we? So we did a lot of algorithms. As I said, I put here neural network in parentheses. That's what we're going to do next week. We have some understanding of the theory of learning. And what we've done last time is basically showed the relevance of the theory, how the theory impacted probably the most successful linear learning algorithm we know of. Today, we're going to spend the time on yet another lesson like this, where I'm going to start with a theoretical question and develop the theory of boosting. Okay, so what is boosting? So today, boosting is a general learning paradigm that allows us to develop a strong learner as a function of many weak learners. And for you now, strong learner and weak learner are non-technical terms. Strong is probably good, weak is not so good. In a few minutes, these will be technical terms. Now, it did not, and boosting today is one of the best general purpose learning algorithms. Typically, people use it over weak learners that are small decision trees, or what is called sometimes decision stumps. Decision stumps is not a well-defined notion. Some people define it as decision trees of depth 1, and in the homework, we define it as decision trees of depth 4. So you can, it's a moving target. But the idea is that you have a collection of weak learners, and you put them together in the right way to get a very good learner. Now, the original boosting algorithm was proposed really as an answer to a theoretical question in PEC learning. People that are really interested in this direction should go to this paper. It's a beautiful paper from a few years ago, The Strengths of Weak Learnability. And it has many other conclusions about learning, the relation between learning and compression, and so on, which I'm not going to get into. What I want is to get to the algorithm. So today, as I said, boosting is viewed as a member in a family of ensemble algorithms, algorithms that make predictions by combining predictions of other simpler algorithms. But it has much stronger guarantees. Actually, under some assumptions, it's guaranteed to learn what you want it to learn relative to the other members of the ensembles. Again, this is a pointer to a demo that you can click on. And what I want to do today is really give you mostly a definition of the algorithm, an example, and some insight into the theory of boosting. I'm not going to go into all the details, even though it's rather simple, but just point out a few insightful components there. Okay, so how did it start, or what is the motivation? So this is the previous version of How May I Help You? You call a company and you want to get some service, and rather than get a person, so this is something that worked in the 90s. It's an AT&T service from the 90s. And their goal was to automatically categorize the calls that come in. And they figured out that they cannot do this well. So here comes a call, someone says something, how to send it to the appropriate person. On the other hand, they found that it's easy to find rule of thumbs that often can be correct. So if the name card was mentioned, it's probably someone that deals with calling cards, something that, but on the other hand, they couldn't learn a single highly accurate hypothesis. So this was the motivation, or one motivation for thinking about the practical application of boosting. The algorithm, then went like this. You have your data set, you select a small sample of examples, you derive a rough rule of thumb that works well for this subset of the examples. You take another subset of the examples, you derive another rule of thumb. Think about rule of thumb as a very simple hypothesis. You do this capital T times, and then you combine the simple hypothesis that you learned into one good hypothesis. So of course, the key questions here is how to choose these subsets of examples, and then how to combine these simple hypotheses, simple rules of thumb, into a single prediction rule. So boosting gives a general methods for doing it with the guarantees that what you're going to get at the end will indeed be a good learning goal. So this was, so I gave one motivation, which is kind of the practical motivation. Really, the algorithm started with a theoretical question. So to remind you, we defined PEC algorithm, which today I'm going to call strong PEC algorithms, that said for any distribution, for all positive small numbers, delta and epsilon, given polynomially many random examples, an algorithm is a strong PEC algorithm if it can find hypotheses with errors less than epsilon with probability at least 1 minus delta, right? So with high confidence, at least 1 minus delta, we're going to find a hypothesis that makes little error. That was PEC. Now I'm going to define a weak PEC algorithm, which is going to be the same, only that this time epsilon is not going to be as small as I want, but rather it's only going to be bounded away from a half. Okay? It's less than a half minus some small fixed gamma. So I'm going to make less than 0.45 or 49% mistakes. Okay? I'm a little bit better than chance, but bounded away from chance. So that's still non-trivial, because chance is trivial. You just decide whether it's positive or negative, but it seems rather weak. And the theoretical question that was asked, so this is one of the questions that Michael Kearns actually asked in his PhD thesis. Does weak learnability imply strong learnability? So let's assume I tell you, here's an algorithm. It can always do better than chance, which seems non-trivial, right? Always can do better than chance. Whatever input you give it, whatever distribution the data is coming from, you can always do better than chance. It seems non-trivial. Can you then boost it to become a real good learning algorithm that for all epsilon is going to do it? So the answer in 88 or 89, when in Michael Kearns' thesis was, we don't know. But it was actually very interesting, I don't know, because what they were able to show is that over the uniform distribution, the answer is no. Now, if you think about it, when we talked about PEC learning, we talked about the significance of the distribution-free assumption. the fact that you don't know what distribution you're going to get the data from. What they showed is that if your algorithm is a weak learning algorithm over the uniform distribution, you can do everything you want over the uniform distribution, you cannot boost it. Which kind of leaves it open, because often when you do something with a learning algorithm, you transform the data, as we've shown in one example, you change the input distribution. If you remember when we gave an example of transformation of features, we show that the distribution over the features actually changes. So maybe it's not surprising that if you fix the distribution, it's not as powerful. And indeed, a year later, Rob Shapiri actually proved the first boosting theorem and gave the first boosting algorithms. The idea was that he had a weak learner. He called it 3 times over 3 modified distributions. So he used the fact that the distribution is any distribution. And he showed that he can get slight boost in accuracy, better epsilon. And then this can be repeated multiple times until you get whatever epsilon you want. So after that, Yoav Freund gave the optimal learning algorithm for what he called boosting by majority, essentially another boosting algorithm that is different than the original one. And a few years later, when they started to work with it and try to apply it on relearning problems, they realized that these 2 algorithms are not practical. They cannot really use them. And in 95, they developed the AdaBoost algorithm, AdaBoost for adaptive boosting, that has really strong practical advantages, very simple algorithm, and the rest is history. So this really had huge impact. I mean, thousands of papers followed up, thousands of applications, if not more, really very impactful algorithm. There are actually 2 important lessons here for PhD students. So I'm going to stop and give you the lessons. I think it's kind of interesting. One lesson is that even though someone solved the problem with a very, very beautiful result in 89, it doesn't mean that you should stop working on it. You can give a better or a different solution, and it's still useful, because the solution that was given by Yoav Freund was different, solved the same problem, but eventually merging these 2 algorithms gave this very practical and important algorithm. So that's lesson 1. Lesson 2 is when they sent this AdaBoost algorithm in 95, or AdaBoost paper in 95, it was rejected from major conferences because people told them, well, it's been solved before. Here are 2 other boosting algorithms. Why do we need a 3rd one? Eventually, it appeared in a low-level conference, but really had a lot more impact than all the previous results in this area. So be patient. It doesn't mean if it gets rejected, it still doesn't mean it's bad. Okay, so now that we have these lessons, what is boosting? Formally, here is the algorithm. We're given a training set, M examples, M labeled examples. Yi is plus or minus 1. And the algorithm is going to run this way. For capital T rounds, I'm going to construct a distribution, dt, on the examples. I'm going to find a weak hypothesis, what I called before, rule of thumb, on this input. Let's call this hypothesis h lowercase t. I'm going to do it such that the error of this hypothesis, epsilon t, is called epsilon t. Now notice that it's really important that I have this distribution dt, because error is measured as a function of the distribution, right? Error is a weighted thing. It's not just counting how many mistakes, but rather it's a probability over a distribution that h is different than the label y. And I'm going to do this t times. So I'm going to generate capital T hypothesis, H subscript T. And at the end, I'm going to output the final hypothesis. So that's the general algorithm. And now we need to attend to a few questions. How exactly to construct the distribution, and how exactly, as a function of it, to construct the final hypothesis. Okay, so what is going to be dt? So I'm going to start with d1, which is uniform distribution. So the weight of the example, the ith example, is 1 over m. M is the number of examples I have. And then every time, I'm going to update my distribution. So essentially, I have m examples. You can think about it as I'm changing the importance of the examples. Right? So some examples are going to weigh more. Some examples are going to weigh less. And I'm going to do this as a function of how well my previous hypothesis did. So given dt and ht, I'm going to define dt plus 1 this way. So I'm going to take dti, divide by some constant. We're going to see later on what is this constant. It's just a normalization constant to make sure that I have a probability distribution. And then I'm going to multiply it by e to the minus alpha t if I did not make a mistake on yi, on the ith example. On the other hand, if I did make a mistake, I'm going to multiply it by e to the plus alpha t. So think about it kind of like we know, right? So if I made a mistake, I multiplied by something. If I did not make a mistake, I multiplied by something else. The third line is just a unified way to write these two lines. So really, I'm multiplying it by e to the minus alpha t yi ht. Okay? So you, again, remember that this could be positive if the sign of ht and yt is the same. It's negative if the sign is different, which means I made a mistake. Same notation that we've been using throughout. Okay, so now I know how to update the distribution, and I need to give you this constant. This constant alpha is going to be half ln log, natural log of 1 minus epsilon t divided by epsilon t. Think about this alpha for a second, and we'll come back to it. And once I have this, the final hypothesis is going to be linear sum of the HTs, where the HT has the coefficient alpha t, and then the sign of this. That's my prediction. Okay? So very simple algorithm. Now, let's start looking at this component here. So the first question here is, what is this alpha t? What can you say about alpha t? What? Like a? Looks like entropy. It is related to entropy. But let's just look at the value. So what do we know about epsilon? Less than a half, bounded away from a half. So which means that, what is this ratio, 1 minus epsilon over epsilon? Always greater than 1. So that's the assumption I'm making. Epsilon is always less than a half, and therefore this fraction here is always greater than 1. And therefore, what I can say is that when I do here e to the minus alpha t, what's e to the minus alpha t? It's less than 1. And e to the alpha t is greater than 1, right? Because think about this. So e to the plus alpha t is really the square root of 1 minus epsilon divided by epsilon. This is directly from this definition, right? The square root comes from this half. E to this is basically this. Because alpha t is less than a half, this guy is greater than 1. So what does this mean? It means that if I made no mistakes, I'm multiplying the weight of the example by something smaller than 1. Smaller than 1. If I did make a mistake, I multiply the example's weight by something larger than y. So basically what happened? I had a set of examples. I learned the hypothesis. Now I'm reweighting the examples. Those on which I did not make a mistake, I downweigh. I don't care about them so much because I already did well on them with the previous hypothesis. Those that I made a mistake on, I'm increasing the weight because I want to focus on them now. That's basically what the algorithm is doing, okay? It changes the distribution because remember, the way I measure error of the hypothesis is a weighted sum over my mistakes. So if I want to reduce the error on these examples I got wrong before, I'm going to increase their error, their importance is going to go up, my algorithm is going to focus on them, okay? So that's basically what this algorithm is doing, very simple algorithm. Now, what is this ZT? ZT is just a normalization factor. I want to make sure that these are distribution, which means when I'm summing up the dt of I over all i's, I'm getting 1. So I'm defining ZT this way. So basically, ZT is just the sum over all i's of dt of I times this e to the what's written here, just to make sure that the sum is 1. So, okay. So you can also think about, because it's a recursive algorithm, when you do dt plus 1, I defined it as a function of dt. You can write it as a function of dt minus 1, dt minus 2, dt, all the way up to d1. And essentially, every time you're going to multiply by this guy here, right? By this e to this stuff. So you really will have that d at the end, dk, is going to be d1, which is this, times product of a lot of e's, e to the power of these guys. Product of e to the power is e to the sum. So you can think about it this way, and in fact, this is going to be an important step in the proof. Okay, let's do an example. So this is my data set. This is my D1. This is the set of examples. I have pluses and minuses. They are all the same size. So think about it. What I'm going to do is actually I'm sampling examples from this data, right? And the likelihood of me getting each one of these examples is the same. So here is my first hypothesis. My H1 is a vertical line that says plus to the left and minus to the right. So I made 3 mistakes. 3 mistakes, and my epsilon 1 is 0.3. Right? Because it's 3 out of 10. And it so happens that alpha 1, if you compute, is going to be 0.42. Now, this is my D2. What happened? Those examples that I got wrong got bigger. The pluses here are bigger. Those examples, the 7 examples I got right, got smaller. It's still a probability distribution in the sense that the total weight of these 10 examples is 1, but these are bigger and these are smaller. So now, I really need to get this right. So this is my second hypothesis. It's a vertical line here. This is my H2. Again, it says plus to the left, minus to the right. So now I have, again, 3 mistakes. These 3 minuses are a mistake. Now, 3 mistakes, just like before, but epsilon 2 is only 0.21. It's clear why? Even though it's 3 mistakes, before 3 mistakes were worth 0.3, now 3 mistakes are worth 0.21 because these are mistakes on things that I got right before, and therefore they weigh less than 0.1. So what am I doing now? Again, I'm taking these examples that are circled here, these 3 minuses, and I'm enlarging them, giving them more weight, and all the other 7 that I got right here, I'm going to reduce the weight. H3. H3 is this horizontal line where I say plus to the top minus to the bottom. And again, I have 3 mistakes. Now my epsilon 3, even though it's 3 mistakes, is even smaller. It's 0.14, again, for the same reason we discussed. And it so happened that my alpha is 0.92. And in fact, that's enough. With these 3 hypotheses, with the alphas as coefficients, what I get is something that looks like this. The green area is positive, the white area is negative. I get perfect classification with a linear function of these 3 weak hypotheses. Questions? Yeah.
What does alpha stand for again?
So alpha is this number that I computed as a function of the epsilon. It's this number. You see here, this is alpha. So once you show me epsilon of the hypothesis, we can just compute alpha. Yes?
Where are you getting the other H1, 2, and 3?
Okay, so that's what I learned. I look at the data. I decided that my hypothesis, my weak hypotheses, are going to be vertical or horizontal lines. That's what I learned. Notice that this is an infinitely large hypothesis space because I can choose any vertical line. I can put it in all x's. I can put any horizontal line, infinitely many. I don't know ahead of time. So at the end, notice that what I got is a linear function, right? This is a linear function. But I did not know ahead of time what are the features of the linear functions. I knew that there are going to be vertical and horizontal lines, but there are infinitely many. Which one are going to be? This is something that I learned adaptively as the algorithm went on. Yeah?
Can I think of alpha as sort of the weights of the weak hypothesis?
Yeah, it's exactly the weights of the weak hypothesis. Only that it's a new way for us to determine the weight. So we learned many algorithms, many linear algorithms, where the weights were determined simultaneously for all features. Here, what we are doing is we are learning the weights one by one because we are determining also the features that are going to be part of my linear function one by one using this AdaBoost algorithm. Yes?
So when we compute the epsilon at each step, the error term, we do it weighted by the probability that it's by the given distribution, right?
By the dt, yeah.
Okay, so that's why it goes down.
Exactly. And that's why you update the dt. That's crucial here. And that is the mechanism that allows you to focus on the hard examples, if you want, those that you missed previously. And if you missed one example for the previous 17 rounds, its weight is going to be really high now, and therefore you're going to try, your new hypothesis is going to try to get it right. Otherwise, it's going to be bad and will not qualify to be with error less than 0.5. Yes?
When you're reweighting each example, what is mathematically happening to that example specifically? Like those three, are you just like multiplying them by like when you just like make them larger, are you multiplying them by like a constant?
Yeah. So the way I'm thinking about it is this way. You give me a data set. I'm thinking, the way I'm going to feed my algorithm is I'm not going to give it all the data set, but rather I'm going to sample from the data set and give it to my algorithm. And you give me a data set of 1,000 examples, I'm going to sample from it 10,000 times. Okay? So if everything is uniform, on average, the algorithm is going to see 10 times each example. That's first time. Next time, I'm going to associate a weight with each example that is different than 1 over 1,000. Some of them are going to be 2 over 1,000. Some of them are going to be 1 over 2,000. I'm going to sample again 10,000 times, which means some examples I'm going to see many times, some examples I'm not going to see. So this is one impact of my reweighting. The second impact is how do I compute the error? The error is the weighted sum of those examples that I made mistakes on, right? Weighted sum of the mistakes I made, which means if at the beginning each example weighed 1 over 1,000, now some of them are worth more, and if I don't get them right, I'm not doing well. My error is larger.
Okay.
Yes?
How does this compare computationally with something like perceptron, where you're adjusting the weight after each guess instead of running multiple hypotheses?
Okay, very good question. So it's good to think about it. So first of all, in perceptron, I have a fixed set of features from the beginning. Here I don't. Right? So here I told you my weak hypothesis is vertical and horizontal lines, but you don't know which. As you go, you decide which vertical lines and which horizontal lines are going to serve as your next weak hypothesis. So that's one difference. So you start with an infinite, in principle, set of features, and you choose them one by one based on which one minimizes the error on the current data set. That's one. Two, the weights are going to be determined incrementally. So if I chose now H3, the weight of H3 is going to be computed directly using this alpha formula that I gave as a function of the error of H. Yeah.
This may be like a kind of in the weeds question, but like when you do this this weighted sum, do you use the prediction of them or like the actual value? So like it may predict like 0.7.
So I'm using the actual value.
So you use like the 0.7,
Yeah.
not the 1.
Yeah. So that's what I do. I put the sign outside here. Okay, so this is the algorithm. It turns out, as I said, to be a really nice algorithm. One of the cool things and an important thing about AdaBoost is that basically what you're doing is all the time you have your sum, the current sum of the hypothesis that you're not using yet, you're going to use at the end, and you keep learning HTs in my notations. Now, it could be that your final hypothesis, let's assume this final hypothesis of 3, H1, H2, and H3, already makes no mistakes on the training data. You can still keep going because the HTs are going to still make mistakes, right? So this linear sum is a lot more expressive than each one of these lines. So it could be that there's just no line. In fact, we know that there is no line that will be perfect on this data. So I can add more H's. And eventually, I will actually improve on the test data, even though my real hypothesis, this linear sum, actually stopped making mistakes on the training data. So it's some kind of a interesting phenomenon that your hypothesis that you're not using really, but you can evaluate all the time because you accumulated it, makes no mistakes on the training. Nevertheless, you can still improve. Okay, so what can we say about AdaBoost? So here is the key theorem, and the key theorem actually has some important insight into how we read things. So the theorem is this: run AdaBoost. Let gamma t be, or epsilon t be a half minus gamma t. So gamma t is a fixed number, and this basically says epsilon t is a little bit less than a half. Then the training error of the final hypothesis of AdaBoost is bounded by, and leave the math now, bounded by this guy here, e to the power of 2 sum over all t gamma t squared. Now, you can appreciate this, or you can just say, you know what, let's forget this and replace all these gamma t's by 1 gamma that is going to be the lower bound of all the gammas, right? So because I have a finite number of t's, 100, so I'm going to take the smallest gamma t, and I'm going to call it gamma. It's still a positive number. So now I can say that the training error is bounded by e to the minus 2 gamma t times capital T. You see? Because I summed over all the t's. What does that mean? Yeah.
It means you want, I mean, it means exactly what it says. It says the training error, like as you make your training, or as you get your smallest gamma, like you want to make that as small as possible. So that kind of explains why you want to run it a lot of times. But like it's also kind of counterbalanced by this T term, which is how many times you run it. So there's like a balancing there, I think.
But either way, that's right. But either way, what you see is that this gamma t is positive, and it's in the exponent. So this is kind of a fixed thing. And as you increase t, as you run AdaBoost more and more times, the training error is going to go down exponentially fast in t. It's going to go down to 0 or close to 0, right? As you add more rounds of AdaBoost, everything is going to be okay. You're going to fit the training data. Which kind of makes sense intuitively because I'm becoming more and more expressive, right? I'm adding more terms to my linear sum, but here we have a guarantee that everything is going to be okay. So now also notice that I don't know what is gamma here. This is the ADA, where the ADA comes in. It's adaptive because all I know is that every round there is this positive gamma t. I don't know what it is because someone promised to me you have a weak learner. Epsilon t is always going to be below a half. Now, one question for you is, why do I care about this? Why do I formulate my theorem here in terms of training error? I don't care about training error. I care about behavior in the future. Yes, so that's spec learning for you, right? So we showed a couple of weeks ago that if you're going to do well on the training data, because what you have here is a relatively low expressivity hypothesis space, everything is going to be okay in the test. So it's sufficient for us to prove things on the test data, on the training data. And this bound really means that as you increase t, things are going to be okay, which is great. Now, we can go into the math, and I'm not going to go into it now, but everything, it's all proved in 3 slides, and everything is spelled out for you. So if people are interested, you can go over it. Basically, mostly is algebra, and everything is explained here. I'm not going to go over it, but I do want to emphasize the last step here, which I called here step 3. The important thing, if you want to understand this, is it really gives you multiple ways to understand or to define error. All this proof is writing the error of the hypothesis multiple ways. What is the error of the hypothesis? It's essentially the sum over the weights of the mistakes that you've made, or the sum over the weighted sum of those examples on which you made mistakes, right? That's error. And this is really what's written there. Other than that, there's nothing. So if you go over this algebra, that's what you should attend to. So let's stop here, and we'll not continue with this, but I do want to attend to this question. So where is this magic coming from? How come I can show a very simple algorithm, and I can prove to you that I'm going to get the training error down to 0 if I continue, and it's going to be a very good learning algorithm. Where is the magic coming from? Suggestion, thoughts? There's no free lunch, right? So we made some assumptions. What were the assumptions?
That you had a predictor, or you had, like, the individual predictors you use are better than a half, what you were saying at the beginning of the lecture.
Right, so the weak learning assumption, if you think about it, is really a strong assumption. What does it say? It says that whatever happens, whatever distribution you place on these examples, there is a weak learner, which means there is a learner that is doing better than chance. Now think about it. Let's see, this example is really a stubborn example. H1 misses it. H2 misses it. H3 misses it. It's okay, but at some point, its weight is going to go so high that some hypothesis will have to get it, right? Because otherwise, the error is going to increase above a half. So this guarantee that there is a weak learning hypothesis, any distribution that you'll give me, I will be able to find a learner that does better than a half on it, better than chance, is actually pretty strong and probably doesn't work in real life. So this weak learning hypothesis seems at the beginning weak, but it's really very strong because of the distribution-free thing, and really is not realistic. Nevertheless, it so happened that this strong assumption doesn't bother other boosts so much, and it really works well in practice. So even though sometimes you will not be able to find a weak learner under these assumptions, you will not be able to find something that does better than chance in some of the rounds or under some distributions. Overall, this algorithm works well. Okay. I'm actually going to skip these two slides also because I want to summarize what we did. Okay. Yeah. So boosting is a member of this ensemble method. Other members in this class are begging and random forests. In boosting, as we said, we start by weighing all the training examples uniformly. And then, as we iterate, we train a model on a weighted training set, compute the error on the weighted training set, and reweigh based on the errors that we made. Typically, this requires hundreds or thousands of iterations. That is, capital T is going to be in the hundreds or the thousands. And the final hypothesis is a carefully weighted hypothesis or carefully weighted prediction of each model. Now, boosting has been studied to death over the last, say, 15 years from many perspectives. So people have shown that you can think about it as a max margin method. You now know what max margin is. People thought about it from logistic regression perspective, which you don't know yet. You'll know in 2 weeks what it is. People thought about it as, different from different statistical perspectives. And each one gives a perspective of why it works well. The bottom line is really the theorem that I showed here, that because of the weak hypothesis assumption, as T grows, things are going to be okay. And the other practical importance here is really that it's a linear classifier, but rather than being a linear classifier over a fixed set of features, it's a linear classifier over an incrementally acquired feature space. Okay, begging. Begging is another way to put together a lot of classifiers. Basically, the idea here is to generate multiple versions of a predictor, and then, as before, use them to aggregate and produce one aggregated function, where what we do is, if your hypothesis predicts real values, you basically are going to average these values. If your hypothesis is going to produce binary values, 0, 1, plus or minus 1, you're going to basically do plurality or majority, depending on its number of categories. So now the question again is, how do you generate the multiple versions? In this case, you generate the multiple versions just by sampling data. So it's called bootstrap replicates of the data. You generate a sample of the data with repetition. So it's possible that the second guy is going to overlap in terms of the training data it sees with the first one. And you generate many of these. You learn, and then you put it together. So really the key reason begging works, and again, it can be explained from statistical perspective, doesn't have the strongest guarantees that boosting has, but has statistical guarantees. And the key issue is that when you sample data, you actually get different results. Every predictor is going to predict somewhat differently. And by averaging this, you're going to get a more stable classifier, so you can explain it via kind of a bias variance type of trade-off. What you will get is something like this. So you have a bunch of decision trees, say. Each decision tree, for example, was generated as one of 100 samples that you've taken. So you learn the 100 trees, and then you average these predictors. So that's one good way to do ensembles. A little bit simpler conceptually than boosting, even though if you think about programming boosting, it's 2 lines of code. Yes? So bootstrap sample just is a statistical term. Well, bootstrap has multiple meanings. One of them, the one that is being used here, is basically you sample with repetition. So that's the statistical notion of bootstrapping. Random forest is another way of ensemble classifiers. I call it here bag trees ++, because essentially it's an improved version of bagging, where what you do is you do 2 things. First, you bootstrap sample of the data, which, again, all it means, sample the data with repetitions. So you have 10,000 example, sample 1,000, learn. Put them back. Sample 1,000, learn. Put everything back. So you always use the whole collection when you sample. That's what it means. In addition, you also sample your feature space. So every tree in this context is going to be learned over a subset of your features. You don't show the learner all the attributes that exist. You subsample them too. So basically, you have more diversity in the predictors. That's the reason that typically, if you want to do random forest, you're going to do this many more times, thousands or more of, times, because eventually you want to get, some of these predictors are going to be pretty bad, but you want to get enough that are good, and then you do the same thing as before. You learn thousands of trees, and you average the results. Yes?
Why can't we just wait to predict each tree according to how well they predict? Take a weighted average.
You probably can by their performance on the training data. You can, only that I don't know that it's going to do better. And no one, experimentally it might do better sometimes. No one has shown that it's guaranteed to do better. You just have so many trees that the assumption is that it's going to do okay this way. But in practice, it could be that sometimes it helps. Basically, that's it. So we talked about ensembles, and I want to spend the last few minutes talking a little bit about multi-class classification. So everything we've done so far in the class, we did for binary classification. It turns out that it doesn't matter, because multi-class classification can always be reduced to binary classification. So everything we said, from algorithms to VC dimension, can be generalized in an easy way to the multi-class case. Now, there are many interesting issues about multi-class. I mean, so it's not only multi-class. You can think about just multi-class. So you want to predict, rather than 0, 1, you want to predict 1 to k. You can also think about multi-label scenarios, where you're allowing to predict a subset of labels. You can think about ranking. You can think about a hierarchy. So your label actually sits on a tree. And you can predict any node in the tree, but it respects the structure of the tree. So think about topics. You have sport as one node, and under sport, you can have football, baseball, basketball, tennis, and so on. And you have politics on the other side, and you will have multiple aspects of politics. The reason this is important is because sometimes you can use a loss function that respects the structure of the tree. What I mean by that is that if you made a mistake between basketball and football, maybe not so bad because there are siblings on the tree. There are two leaves that reside under sport. On the other hand, if you make a mistake between football and politics, you want to get a higher penalty because the only common parent they have is maybe the root of the tree. So this is called hierarchical classification. Now, I'm not going to talk about this. I'm going to talk only about the standard multi-class classification. And the setting here is very simple. We're given a data set, and the labels are 1 to k. The prediction is, given an example, choose the label. And the cool thing is that, as I said, we can reduce multi-class classification to binary classification in a very easy way. And my intention was to talk about 3 paradigms and then move to another one, more general paradigms. I will not have time to talk about all of them, but let's see what would be the easiest way for you to think about how to reduce it. So I give you a black box that is a binary classifier, but the problem that I give you has 7 labels. How would you use it? So what you're suggesting is something that I'm going to call here 1 versus all, which says let's take label 1 as the positive, all the others as negative. Now let's take label 2 as the positive, all the rest as negative, and do this 7 times. How would you predict? So now you're going to learn 7 binary classifiers. How would you predict at the end when I give you a new example? The highest value. So you compute, let's say we have linear classifiers. They produce a dot product, each one of them. I'm going to do argmax, highest value of the dot product. So this is 1 versus all. Learning decomposed to learning k independent binary classifiers. And where I decided to split to positive and negative, as I just said. And this gives me 7, in general, k hypotheses. And I predict doing argmax. So I'm computing w dot product with x and taking argmax. Problem solved. Now, you can think a little bit about it, and you will see here is an example of k equal 3. And really what I'm doing is I'm decomposing it into binary classifiers, binary problems this way, black versus the rest, blue versus the rest, green versus the rest, and everything is good. Is this going to work always? Why not? Here's an example, right? So these red points, you cannot separate from the union of all the other colors. So if you use linear classifiers, and we have to decide what is a reference classifier every time. If I use linear classifiers, this shows that 1 versus all is not completely expressive. I cannot separate it from the others. So there are some problems. I like to think about this problem as kind of a Verona diagram for people that know this thing. So the problem I have is this kind of things. How can I learn this Verona diagram? What would be one solution for this? Give me another scheme that potentially has a chance to solve this.
Use like a more sophisticated classifier.
I can change my classifier. That's one solution. But I can always do this. So moving to a higher expressivity class is always possible. So let's fix the expressivity of the class and think about schemes that make use of that. Yes? Yeah, so again, this is expressivity. I don't want to change the expressivity, I want to change the scheme. So one other solution would be what is called all versus all, which means I'm going to consider all pairs. So I have k labels. I'm going to try to compete, to learn 1 versus 2, and then 1 versus 3, and then 2 versus 3. and so on, all pairs. For each one of them, I'm going to use a linear classifier, right? And then I will be expressive enough. Now, I will have a lot more classifiers, right? I'll have k choose 2 classifiers, quadratic number of classifiers. On the other hand, each classifier is going to be learned from a smaller number of examples. So in this case, positive examples for the ij classifier is going to be I are positives, j are negative. And I'm going to do this for all the I and j's. Now, the decision is a little bit tricky. When you give me a new x, how do I decide? How do I make a prediction? That's a little bit trickier. Any suggestions? So there are multiple ways to think about it. I can do by majority. I take an example. I run it on all the classifiers. If everything is perfect, all the classifiers are correct, one of them is going to win over all the others. The correct one is going to win over the others. I'm done. Everyone agrees? If no mistakes, there has to be one classifier that is going to beat all the k minus 1. This may not happen all the time because it could be noisy. Another way, and also it means that I have to evaluate a lot of classifiers at the end. Other solutions could be to do a tournament. Right? So I can take pairs. I take 1 and 2, 3 and 4, 5 and 6, and so on, and I run their classifiers. And then the winner goes to the next step, and now I have the winner between 1 and 2, compete with the winner between 3 and 4, and so on. So I have just logarithmic number of evaluations. Again, maybe I'm going to get this wrong. So the evaluation here could be a little bit tricky. Now, one thing I want you to think about, and this is going to be my last slide, is think about relative advantages of 1 versus all and all versus all. You can think about it from the perspective of how many classifiers you have to learn each time. Linear in the first one, quadratic in the second one. You can think about it from the perspective of how many examples you're going to feed into the classifier each time. So in this case, you're going to feed all the examples, right? K over M. I'm thinking, in this example, I'm thinking that everything is uniform among the labels. So it's M over K, positive example, and the rest negative, K times, versus M over K positive and M over K negative, but K squared times. So this classifier are going to see less examples, but there are many of them. So which paradigm should I choose? Actually, it depends a little bit on your data. And one thing that I want you to think about the trade-off that we discussed when we talked about dual and primal. And we said that one of them is better or more advantageous when you have a lot of examples. One of them is less advantageous when you have a lot of examples. And the same kind of trade-off comes to play here. And indeed, if you look at some packages, for example, liblinear, which is the best SVM package, you will see that they were smart enough to decide that when they run in the dual space, they're going to use all versus all rather than 1 versus all, which is the more commonly used techniques. Most people, when they run multiclass, are going to do 1 versus all. This is the standard. All versus all is sometimes better, especially when you run in the dual, when you have a lot of examples, when you don't have a lot of examples. Okay, I'm going to stop here. There are a few other things to say about it. Next week, as I said, is going to be devoted to neural networks. And please come to talk to me about the projects.
So what should we do regarding the rebate thing? Should we allow people to create
Maybe ask them again. I don't want to make it public.
Yeah, but how is the rebate going to should I take the exam from your office at 5 to
Yes, I'm going to be there. Yeah, I'm going to be there. Yeah. And by the way, so I started to alphabetize it. Like that. Someone came to take my little bit of the mess. I didn't finish. So maybe I finish before you come in.
Okay, so what I did was I put A to J in one stack and another one stack.
Yeah, but it's still, of course, when I was looking for his exam, this was the last one.
I am here. Yeah.
So I had problems just before sharing this one. I tried again.
Because I will be rewriting the paper. You have USB-C today because of one question.
Do you have HDMI?
Yeah, one question.
Yeah. HDMI. Okay, I'll do HDMI.
Yes, and Thunderbolt. I'm out because without all I can do it that time I will do it. Otherwise, I will do it. Otherwise, the next person can.
I recently upgraded to USB-C, which is also
some people have different
nice.
answers, so I just have to check it. Eventually,
Yeah, it's a lot of dongles.
If you need help, let me know tomorrow. I'll be here.
Oh, 9 tomorrow?
Never had any dongles.
Yeah,
I will try it. It's not.
Yeah, you can put your laptop.
Oh, I know the beat, but
You probably need to put it over there to get.
but I will tell you like what to be needed.
one interface to rule them all. What time do you get in tomorrow?
I already have a meeting now.
Oh. Because it was talking about grading one of the questions.
Oh, so when do you want to meet?
No, what I'm thinking is that his office hours are at 9 tomorrow, so he can regrade it in those office hours. I will regrade what I can in today.
So just come to my office
Okay.
a few minutes before 9.
Okay.
So your office hours is 5 to 6. Yeah, and I'll be there at the same time.
Yeah, say it.
So I told you,
And
he said that you were going to do this as a
file I
project.
sent, I
Yeah,
didn't.
that's a code.
Yeah.
Oh, thank you. Yeah, we got
So there's more
the.
deadlines. So if you want to talk about it, let's set up time.
We were
So Steven and I are going to be away next
the other ones were.
So the week after, let's set up time.
Yeah, some places decide.
So you have the date already?
I have the data. So it's English, Spanish, and Egyptian. Course next week.
What do you mean Egyptian?
So it, English course next week. Yeah, so that tweet consists of language English and Spanish, all Romanized, and the second data set is Egyptian and Arabic, all Romanized, all. Yeah. So Egyptian as well as Arabic language.
Just 2 dialects maybe?
I think so. So yeah.
Really? And it's all in Arabic form?
It's all Romanized.
Oh.
I haven't haven't looked at it because I don't understand anything. So I only looked at English and Spanish.
Okay, definitely. But you sure that it's just Arabic and Egyptian?
Okay, I will look at it again.
Because these are very similar.
Yeah.
So it's really dialect, Egyptian dialect.
Great. And then there's a mic, a wireless mic.
Yes, definitely have to wear this. But we can look at it together with the video. So you want to focus more on the Spanish English?
Because I understand it.
Did they explain to you that we're recording this?
Yes,
And that there's,
I did sign.
we're recording the slides and your voice, but not a picture of you.
Okay, I mean, I'm fine with my picture being recorded as well.
But there's no blackboard, there's no you, just the slides and your voice, and they're synced together.
That really
And it's on a timer.
is fun.
So it starts, I think, at 3:05. That's when the timer kicks in.
So do you want to check everything is working or?
Yeah, you tap on it, you'll hear it.
Okay,
Yeah, well,
Okay.
good.
it's
Did you
good.
have audio in your show?
No, no idea.
Well, you sound real good. This is a very nice, clear digital microphone. It's in the post-digital age. You see that go by? You know, they took the TV spectrum, right? The old analog TV spectrum. They gave that to the people, and they make it all digital now.
Yeah.
Wireless microphones had the same deal go by. Old tech, maybe mid-2000s, was the last years that you were allowed to have these analog frequencies. And then FCC took them all. Those are all verboten. You're allowed to use these digital frequencies. This is one of those. But it's really nice. It's a wonderful, low noisy kind of thing. Just curious.
I feel, yeah, the rest of them works well. The one thing
Well, we're scheduled to renovate this whole room. I mean, the projector's on. You can't turn on without projector.
Yeah, I know, they look like two different projectors.
It is two different projectors. That's completely what it is. So, and if you want to use it,
Calibration.
if you want to use it, you have to go and call me. I have to come and turn it on and turn it off.
Okay, yeah, I teach engineering.
Yeah,
And I just
most-
learned, okay, just right.
That's only one more semester.
Okay. Oh, yeah.
I really
Easier to stick with that than
I wish I had a 60 by 9. You know, it's a great big kind of movie theater.
the widespread.
Okay, well. Okay, let me show you this, since you might not have seen it before. It's me. Jackson knew what to do.
Yeah, you go to your tutorial like, that'll be $3.99. For the food truck, don't think it's a food truck.
Okay, great. But yeah, is there anything else in the bio you wanted me to mention?
Just my name would be fine.
Yeah. Sajid? Zahidi.
I mean, either way.
Okay.
I'm pretty sure nobody can pronounce it the way I pronounce it back home, so Zahidi.
Right.